Using a linked list to implement a stack. A stack is a data structure that follows the last in, first out principle, where the most recently added element is the first to be removed. Using a linked list, we can efficiently implement a stack by utilizing the head of the linked list as the top of the stack. The operations and type complexity for that is number one, push. Push an element onto the stack, create a new node, and insert it in the head of the linked list. Time complexity equal 1 because inserting a head does not require transversal. Pop. To pop an element from the stack, remove the head node of the linked list. The time complexity for this one is big O1 because removing the head involves only updating the head pointer. Get top. To get to the top element of the stack, simply return the value of the head node without modifying the list. The time complexity for this one is big O1 because no transversal or modification is required. Finally, is empty. To check if the stack is empty, verify if the head of the linked list is null. The time complexity for this one is big O1 since it's a simple pointer comparison. Part number 2, using a linked list to implement a queue. A queue is a data structure that follows the first in, first out principle, where the first element added is the first to be removed. To implement a queue, in a linked list, use both head and tail pointers. The head points to the front of the queue, and the tail points to the end of the queue. Operations and time complexity. In queue, to add an element to the queue and create a new node and append it to the tail of the linked list. Update the tail pointer to the new node. The time complexity for this one is big O1 because appending to the tail involves no traversal of the tail pointer, and the tail pointer is maintained. Dequeue is to remove an element from the queue and remove the node at the head of the linked list, and we update the head pointer to the next node. The time complexity for this one is big O1 because removing from the head only requires updating the pointers. Size. To get the size of the queue, maintain a counter that is incremented during the enqueue and decremented during the dequeue. The time complexity is beta 1 because the counter is updated during the enqueue and dequeue and no traversal is needed. Is empty basically is to check if the queue is empty and verify if the head pointer is null. The time complexity is beta 1 because it's a simple pointer comparison.